Okay, so I'm going to go over 6.5 because there were a lot of problems with it or a lot of questions that came up during recitation. So real quick, going back over the problem, there was two different pHs at 7 and 10.5 that were given. The temperature was 293 Kelvin. Some things to remember is that joules are equal to kilograms meter squared per second squared. And then the specific volume for the protein was 0.749 centimeters cubed per grams, and then of course the density of water is 0.9982 grams per centimeter squared, or cubed. So if you went through your book, you would be able to find that there is this equation that shows for the ln of a concentration at a certain radius and ln are divided by the ln of a concentration of another radius. You can actually get this equation for omega squared times m times 1 minus the specific volume times the density of the substrate divided by 2 kT. And we know that our r squared value is 50 and 49 for what we're looking at. So that's our starting and our final. So if you go ahead and plug those in, we had the concentrations that were given in that table, so you could plug that into the ln portion of it. You needed to convert the RPM that was given in the question to radians per second, and then you could plug that in. And then you can go ahead and multiply out the rest of it. So for our K value, we're going to use the 1.38 times 10 to the negative 23 joules per K, and we'll multiply that by our Kelvin. And then again, we'll just subtract the 50 minus 49. So when you do this, all of your units actually end up canceling out except for the grams, and then you need to multiply by Avogadro's number to get into grams per mole. And then you can solve for m at that point. And so the m at the pH of 7 was 68,827 grams per mole. And then if you do this for the 10.7, you get the 17,136 grams per mole. So you could have also left it in grams, but it looks a lot nicer if you put it in grams per mole. Overall, it just works a lot better for what we're doing. And then when we move on to the graph portion of it, we are going to be looking at the different graphs that we were asked for. So there's size exclusion chromatography. So remember, size exclusion, the bigger things run off first. So that pH of 7, which was a lot bigger, 4 times bigger actually, would run off a lot faster than our pH of 10.5. And then for the other two, they're pretty self-explanatory, and most of you got that exactly right. And then at a pH of 9, it could not be determined. So that was a little bit tricky because there was nothing in the question that gave you information about a pH of 9. So you don't know if it was forming a dimer at that state or what was going on. You wouldn't be able to tell based on the information given to you. If you were going to be expected to do that, there would be some information about how the molecule actually forms in order to determine what you should draw for a pH of 9. So hopefully that helps and helps explain a little bit of the math behind what was going on.